Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. And this short video, another video in our series of videos dealing with functions, is going to look at, once again, injective functions. Okay, and in this example, we're going to have an example of a function that is injective, and we're going to prove that it's injective. But before we get there, let's just provide the definition of what we mean when we say that a function is injective. Well, if we want to test to see whether a function is injective, we must have the function in the first place, okay? Which means that the function must be well defined, we must know its domain, and we must know its codomain. So let's assume we have that information. So let A and B be non-empty sets, okay? So let A and B be non-empty sets, and let F be a mapping from A into B, okay? So let that be true, okay? Then we say that F is injective, okay? If for all x1, x2s that are elements of the domain, so if for all values that we choose from the domain where we can choose two, for all choices when we choose two values from the domain, okay, we have the following, okay, if that makes sense, okay. So we have the following, okay. If x1 is not equal to x2, well then this implies that f of x1 must not be equal to f of x2. And that's our first definition of injectivity. It says when you choose two different values, okay, from a particular domain, and when you map them two values into the range or into the codomain, okay, what we're going to have is, what we should arrive at is two values that are different within the range itself. Okay, that's one definition. An alternative definition, which is the definition I'm going to use for this particular proof, says that if f of x1 equals f of x2, in other words, if we have two values that have been mapped to the same position in the range, well then this implies that x1 must be equal to x2. Okay, that x1 must be equal to x2. So there's our two definitions. We have this way of testing for injectiveness, okay, and we have this way of testing for injectiveness, okay. So we have two ways that we can go about testing to see whether a function is injective. So let's do another example. So let's consider the function, okay, the function defined as follows, okay. It's a function f, and it's defined to take the integers into the integers, if that makes sense, okay. And its specification is f of x is equal to 3 to the power of x, okay. So that's our function there, and the question I have is f injective? Is it an injective function? So that's a question that we have, okay. Is it an injective function? Well, look, here's the definition of our function, okay. This is the definition. We've been told its domain and its codomain, and we've been given the actual implementation of the function. So let's see, can we test to see whether this is injective or not, okay. And let's rely upon this particular approach to show that it's injective. Because if a function is injective, well then if we have two values that are mapped to the same place, well then what that implies is the two values must be the same, okay. So let's say let x1 and x2 be elements of the integers. In other words, let's choose two values from the domain. They could be the same, they could be different, we don't know at this particular stage, and let's see what the consequence is of this particular choice. So let x1 and x2 be any two values in the integers, and let's do this. Let f of x1 equal f of x2, and let's see what the consequences is. Well, what does that imply? That implies that 3 times x to the power of 1, okay, because that's what f of x1, that's where x1 will be mapped to under this function. Let me map to 3 to the power of x1 must be equal to 3 to the power of x2. Okay, so that's an implication of us mapping x1 and x2 under f to its range value. So what we get is, within the range, the actual value that's mapped to is 3x1 and 3x2, 3 to the power of x2. Well, now, what does this imply? This implies that if we get the natural logarithm, okay, of both sides, the natural logarithm of 3 to the power of x1 must be equal to the natural logarithm of 3 to the power of x2. Now, we know a side aside, okay, we know this particular fact is that the ln of a to the b is the same as b times the ln of a. Okay, that's just a fact that we know from logarithms. So what does this imply? This implies that x1 times the ln of 3 must be equal to x2 times the ln of 3. Dividing across by the ln of 3, they cancel out, so this implies that x1 must be equal to x2. Okay, which is our proof done. So what we've actually shown here is that when we choose two values from the domain, okay, choosing two values from the domain, and when we assume that the two values are mapped to the same place, okay, under some deduction, what we can actually arrive at is that the two values must have been the same in the first place, okay. And this is effectively our proof that the function f of x is equal to 3 to the power of x is in fact an injective function. Okay? Because if we assume that the two values from the domain have been mapped to the same place, that's what f of x1 is. F of x1 is a place in the codomain, or it's a spot within the range. F of x2 is a place within the codomain also, or more specifically, it is a spot within the range of this particular function f. So what we have is two spots within the range. We're setting them equal to each other, which implies this from the definition of the function, getting the natural logarithms of both sides, and relying upon the definition of the log of a to a power, okay, we end up with this fact here, which tells us that x1 must be equal to x2. This being a consequence of us setting the two values equal from the very start. So what we've actually shown here effectively is that the function f is injective, if that makes sense. So hence what we have is f is an injective function, okay? And that's our proof done in this particular case. Okay guys, once again, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope that this video was in some way intuitive, and more importantly I hope that was helpful for you, and thanks for watching. Okay, bye bye.